Good morning. I'm Jimo Lee, presenting a comparative study of deep learning models for stellar classification using SDSS-72 data. Classifying stars, galaxies, and quasars is a fundamental to cosmology, but surveys produce millions of objects, making manual labeling impossible. My approach is to compare eight deep learning architectures. Three attention types matter here. Self-attention links all wavelengths. China attention weights bands. Spatial attention targets spectrogram regions. Each highlights the lines that drive classification. Notice the redshift gradient. Stars near 0, galaxies to 1.5, quasars beyond 2. Redshift itself is a strong prior through, though heavy galaxy bias forces handling imbalance. A stellar spectrum is a fingerprint of its outer layers. Hydrogen and calcium absorption reveal compositions and temperature. Galaxy light integrates billions of stars, so absorption features smear rather than sharpen, making galaxies harder to classify than single stars. Quasars look entirely different. Broad emission lines come from a gas accreting into a supermassive black hole. These are the strongest Q a classifier can exploit. Here, a star appears as a clean point source. For nearby stars, photometry alone often suffices. Galaxies show extended structures, spiral arms or elliptical halos. Morphology is easy to give away when imaging is sharp. A quasar looks like a star in imaging. This is exactly why spectroscopic features become essential. All three classes overlap somewhat in UG versus GR space. This residual ambiguity is precisely why color-only models plateau on near 87%. Stars and quasars look identical in imaging, only galaxies are visually distinct. This morphology collision is exactly why spectroscopic features must resolve. PCA. The first two components hold 96% of variance. Stars cluster cleanly, but quasars and galaxy clouds overlap substantially. Linear projections fail. We need nonlinear models. Multicolored photometric analysis, each panel reveals different separability. None alone is sufficient, justifying use of all 5 bands plus engineered color indices as inputs. I benchmarked the full spectrum from shallow ensembles to transformers. The proposed anti-attention efficient adds multi-head self-attention on top of an efficient convolutional backbone. A clear hierarchy emerges. Tree methods cap near 90%, standard CNNs reach 94%, attention efficient exceeds 95%. The gain comes from resolving quasar-star confusion. Multi-head self-attention contributes the largest jump, plus 1%. Class-weighted loss actually hurts the performance, suggesting that in a naturally separable space, force rebalancing introduces biases. The model reaches 95.7% accuracy with under 5 million parameters, deployable at survey scale. Future work explores imaging, transfer learning, and interpretability. Thank you.